Continuing our work with probability, let's jump back to section 6.1 for a few minutes. We've established the basic ideas, but now we need to go back and just add a little more to it. The ideas of probability really don't get any more complicated. What gets difficult is counting. How many different options? How many events satisfy? How many total number of options are there? So let's just go backwards and talk a little bit more about counting. So I've written a little problem up here. We're thinking about Restaurant Week and how different restaurants offer different specials to try and entice you to come in and try their restaurant. So I made up one little example where a restaurant offers us 3 choices for appetizer, the choices being salad, soup, or cheese, 4 choices for entree, fish, steak, chicken, or vegetarian, and 2 choices for dessert, we'll have ice cream and cake. How many total different meals are possible? What I'm going to show you is a basic tree diagram, and if we make our tree diagram, we could get every single possible option, and then at the end count the number of trees or branches that we have, and those are our total number of total meals possible in this case. So the first thing, we start off with an appetizer, and we have 3 choices for appetizer. So up here, these will be the people who pick salad. Here will be the people who pick soup. And then down here, we'll have the people who pick cheese. But now go back to the top. Everybody who picks salad still has the same 4 choices for entree. And they could pick salad and then fish, salad and then steak, salad and then chicken, or salad and vegetarian. Same thing for all the people who pick soup. They can also have fish, steak, chicken, or vegetarian. And lastly, same thing for all of our cheese people. Fish, steak, chicken, and vegetarian. And now every single one of these branches, and if you count so far, 12 total branches, 12 total options thus far, but now every single one of them has their 2 options for dessert. Ice cream and cake. Ice cream and cake. Ice cream, cake, ice cream, cake, and all these people down here. I apologize that my tree diagram got a little messy, and that's typically what happens. But it'll still serve our point in just another moment when we get to the very end. So that covers everything. And now if we look from top to bottom, I could pick any single branch and trace back their entire meal. So if I pick this branch right here, this is a person that had cake, fish, and cheese, or cheese, fish, and cake in that exact order. So now we look down, how many total branches? 24 total branches, meaning 24 different meal choices. We could still now change this into probability. This would be the total number of possible outcomes. Well, what's the probability someone had fish? Well, these 2 people had fish. These 2 people had fish. These 2 people had fish. That would be 6 total people that had fish out of 24, 6 out of 24, or 1 out of 4, the probability they chose fish. So again, a tree diagram helps us see every single possible outcome in our sample space, seeing every single literal option along the way. But you could see, this was not a very complicated situation, but how messy my tree branch really got, and not the easiest thing for us to do. So let's take this one step further. Instead of writing out all the outcomes, oftentimes we just need to know the total number possible, and this leads to the idea of the counting principle. When we have multiple choices, we'll just see the number of choices at each step and then multiply those possibilities. So in this situation, we had 3 choices. We made our choice for appetizer, we had our choice for entree, and we had our choice for dessert. And we had 3 choices for appetizer, 4 choices for entree, 2 choices for dessert, and when we multiply, 3 times 4 times 2 gives us 24 total choices. Now let's get back to probability. So I've got one more written out example for us to consider. We're looking at a bunch of students grouped by their year and their major. So I've got their different classes, freshmen, sophomores, juniors, seniors, and their different majors. I kept this very broad so this chart didn't become too large. We're just looking at science, humanities, and health. Now let's get back to a probability question. If we select one student, what's the probability the student is a junior? Got a lot of information, but it still boils down to what we've always been doing. How many outcomes satisfy out of how many total outcomes? Here, this chart had a lot of information, but it doesn't have any of the totals. We should understand this chart that there are 27 freshmen who are science majors. There are 181 sophomores who are humanity majors, 41 juniors who are science majors, 77 juniors who are health majors. I could do this for every box, but just the point to make sure we understand. So if we want to know the total number of outcomes, it would be the total number of students. So we could add all the freshmen, all the sophomores, all the juniors, all the seniors and get that total, or add all the science majors, all the humanity majors, all the health majors. But either way, the total number of students is the sum of all of this. So I'll just take a moment, just doing it on my calculator. I'll make a note. So went this way. I had 152 science majors. I have 816 humanities majors, and then for my health majors, 317. So when I add those together, that gives me a total of 1,285 students. Notice I could have done the same thing if I added all the freshmen together. I would have had 319 total freshmen, then 315 sophomores, 330 juniors, 321 seniors, which gives us the same 1,285 students. So, again, didn't have to do all this, just a good thing to point out. Getting to this problem, I needed the probability of a junior, total number of students is the total number of possible outcomes, and my total number of juniors. Like we mentioned earlier, nothing wrong with leaving that as a fraction, but certainly no harm in rounding that to a probability. Just notice, as I did that arithmetic, I got a very ugly decimal, but I just rounded to the 3rd decimal place. Good habits, as we've always said. 3 significant figures is a good thing, especially with probability. And I should have mentioned this at the beginning, our probabilities are unitless. It's all just about that idea of chance. So let's keep going with this example for a few more, and then we'll get a few final properties that we'll finish up with. So, still selecting one student. What's the probability their major is health? This is just like the first one. We're just going to look over now, thinking about all of our total students. So the probability of health major, we still have 1,285 students to pick from. And now since I've already done the hard work, I already know there are 317 health majors. Those 317 out of 1,285. Which again, nothing wrong with that fraction, just trying to get us used to the decimals, and that one would be 2.247. Let's keep going. Still selecting one student. What's the probability they are not a health major? Since we've already done so much of the arithmetic in the first part, we could look at it, well, if there are 317 health majors, 1,285 students, so when I subtract those two, I'd find out there's 968 non-health majors. Looking at the portion that are health majors, subtracting that from the total number of people we had available, or we could have just started adding the humanities and the science majors to get that total number of non-health majors. This is, again, that idea of the word not here is getting us back to that idea of a complement. So the probability of not health majors, 968 out of 1,285. And that gives us 0.753. And not a coincidence that these two values add to 1. Let's stick with this for just 2 more moments here. Let's look at 2 more complicated problems that we'll get to a little bit later. Everything is still basics of probability, but let's start peeking ahead. Section 6.4, 6.5, 6.6 start taking us a little further, looking at and, or, conditional probability, but it's still the same idea, everybody, so let's take a look at that. Still selecting one student. What's the probability the student is a sophomore and is a science major? This may look a little ugly at first, but this is actually an easier problem because we just have 2 things to consider. We still have the same 1,285 students, but we're getting 2 things. We're getting an and statement here. The book can go pretty nutty with its notation in these sections, but it's just looking at who satisfies. We come to the top. I'm not looking at all sophomores. I'm not looking at all science majors. I'm looking at people that are sophomores and science majors. I'm only considering these 53 people. So this probability would be 53 over 1,285. That is a big difference between saying and versus saying or. What's the probability the student is a sophomore or is a science major? The or makes all the difference. Now, any sophomore qualifies, or any any science major satisfies. The only thing is just to make sure we don't double count. So it's easy to just go back to the top and go, there's 315 sophomores and there's 152 science majors, and add those 2 together to say, what is that, 467 people that satisfy, but realize we counted these people twice. We counted them as sophomores, we counted them as science majors. So we could just start from scratch, or eventually we'll get a more complicated formula to go with this, where we'll find the probability of each of these and subtract the overlap, subtract where they intersect, or we could just take a basic approach. We've got 152 sophomores, just looking at the total sophomores. And then when I look at my, I'm sorry, that wasn't sophomores. That was 152 science majors. I'm sorry. And then we could just get the other sophomores that we didn't already count. So I'm getting an extra plus 181 plus 81. These are the extra sophomores that were not science majors to give us a total of 414 students that are either science majors or sophomores. So the probability would be 414 over 1,285. The last question here, and then again, we'll just get some quick properties before we move on, is an intro to conditional probability. Assuming we selected a senior, what's the probability they are a health major? The biggest difference in this question is the extra assumption. Now we're not looking at picking any student from our group. We're specifically assuming that we selected a senior. So basically going back up to our chart, everybody up here is now not being considered. We're only looking at the seniors. So compared to the other problems, it's the denominator. We're not looking at randomly selecting a student, so having 1,285 to pick from. We're assuming we selected a senior, so we only have 321 to pick from. So this probability will be out of 321. This is what I always said. I always like to start with my denominator first. Think about who we should consider, who is the total number of possibilities that could come up, and now think about who satisfies. So out of these 321 students, the only one out of these students that are health majors are these 63. 63 out of 321. And now we'll finish with some basic properties, everyone. This comes right out of our book. This chart, where we get these properties, and this is something we really want to get accustomed to. So any probability we look for, if we're setting up these fractions, we can never get a value lower than 0. We can't get negatives here when you're looking at how many things satisfy out of how many total possible outcomes. And we can't get a number bigger than 1. You can't have more things that satisfy out of the total number of possible things that could possibly happen. So we always get values between 0 and 1. If we take the whole sample space, the probability equals 1. That's what we're starting to see with the idea of the complement, that if you could break it down into 2 possibilities, their probabilities have to add to 1. Get a few more properties here, and then we get these ideas of complements. If we know the probability of one thing, then we could find the probability of its opposite by doing 1 minus. If there's a 30% chance of rain, that means there's a 70% chance of no rain. So 0.3 probability it does rain, 1 minus 0.3, 0.7 probability it does not rain, what we saw earlier. And the last thing that I wish they pointed out here, the probability, if it equals 0, means the event will not happen. Not that it's not likely, that it will never happen. You roll a die, what's the probability you get blue? The die only has numbers on it. It doesn't have colors. You're never going to get a color. The probability is 0. Similar, if the probability equals 1, that doesn't mean that it's just likely. That means that it's guaranteed to happen. You roll a die, what's the probability you get a number? You're always going to get a number. The probability equals 1. We'll continue and get more practice with these ideas.